So now we look at the current equivalent to Thevenin's. This is Norton's theorem. Like Thevenin's theorem, Norton's theorem provides a method of reducing a more complex circuit to a simpler, more manageable form of analysis. The basic difference is that Norton's theorem gives an equivalent current source rather than a voltage source in a parallel rather than series with equivalent impedance. So the form of Norton's equivalence can be shown in the diagram to the right here, 1931. You can see a current source and you can see a equivalent Norton's impedance across the output A and B. Regardless of how complex the original circuit is, it can be reduced to this equivalent form. The equivalent current source then is designated I sub n, or I Norton, and the equivalent impedance is Z sub n, or Z Norton. Lowercase italic subscripts denote AC quantity. Okay, you should have learned some of this in your DC course in 131, and so now we're seeing the equivalent for AC circuits. Norton's theorem shows you how to find I Norton and Z Norton. Once they're known, simply connect them in parallel to get the complete Norton equivalent circuit. So for the circuits viewed from terminals AB, we can find I Norton to calculate the current between terminals A and B with the terminals shorted. Okay, and we can see that in the diagram to the right here. We see the AC circuit, we see AB and a load resistor. We remove the load resistor and short the output. So let's take a look at an example. We want to determine Norton's equivalent, I Norton, for the circuit as seen by the load resistor. The beige area identifies the portion of the circuit to be Nortonized. So we can see that here. We've got a load resistor across AB. We've got two capacitors, X sub Ci, X sub C2, in their reactive values, 50 ohms, 100 ohms, and a resistor of 56 ohms. The source is 60 at an angle of 0 volts. So we remove the load resistor across the output and short the output. So I Norton is the current through the short and is calculated as follows. First, the total impedance viewed from the source is. So we go through and we calculate X sub C plus the product over the sum for R and X sub C2. So those two sum together across, forming the parallel of X sub C2 and the resistor. 50 at an angle of minus 90 degrees for the X sub C1, and then 50 at an angle of minus 0 times 100 at an angle of minus 90 over 56 minus J 100 ohms. So just like before, we do our polar rectangular conversions to allow us to manipulate and solve for this expression. So 50 at an angle of minus 90 degrees in ohms is unchanged, but when we go through and first convert the denominator to polar forms and then multiply the terms in the numerator, 50 and 100, and carry the angle through minus 90, in this case minus 100, we end up with 50 at an angle of minus 90 degrees ohms plus 48.9 degrees at an angle of minus 29.3 degrees ohms. So from that, we can convert those polar coordinates or those polar expressions to rectangular expressions. Minus J 50 ohms plus 42.6 ohms minus 23.9 ohms as a J. So 42.6 ohms minus J 73.9 becomes our impedance in rectangular form. Converting then to polar form gives us 85.3 at an angle of minus 60 degrees in ohms. So again, we continue with our conversions to come up with our correct answers. Next, then we calculate the total current from the source. So the I source then is equal to V source by that total impedance. So 60, that should be 60 at an angle of 0 volts, 85.3 at an angle of minus 60 degrees in ohms gives us 70.3 at an angle of 60 degrees now in milliamps. Finally, we apply the current divider formula to get I Norton, the current through the short between terminals A and B. So our current divider expression, product over the sum, in this case we're only looking at the current divider of R and R plus X sub 2 times the source current. So 56 ohms and the 56 ohms minus J100 in the denominator. We multiply that times the I source that we just calculated, 70.3 at an angle of 60 degrees milliamps. Gives us then 34.4 at an angle of 121 degrees in milliamps. This then is the value for the equivalent Norton source. Norton's equivalent impedance then is defined as the same as Z Thevenin. It's the total impedance appearing between two specified terminals of a given circuit viewed from the open terminals with all sources replaced by their internal impedances. So to find Z Norton for the circuit below, we view it from the open across the terminals AB. So now we're going to zero out the source, short it out, and remove, if we had a load here, in this case we've got an open between A and B, the same values that we had before. So looking in between the terminals A and B, capacitor 2 then is in series with the parallel R and capacitor 1. Okay, so now what we need to do, like we did before, we end up with Z Norton is X sub C2 plus the product over the sum R and X sub C1 gives us a value of 100 ohms at minus 90, and then the product over the sum, we do our conversions in the denominator to polar so that we can solve the second expression. We end up with 100 at minus 90 degrees in ohms plus 37.3 at an angle of minus 48.2 degrees in ohms. Put everything in rectangular form then, so now we convert 100 minus 90 becomes minus J100. Some of these you should be able to look at now fairly quickly and determine that we have a plus or a minus J. In this case we have minus 90 degrees, so you can see we have minus J for our 100. 24.8 ohms then becomes the real part of the second expression. Minus J 27.8 ohms is the imaginary part of the second expression when we do our conversion, and we get 24.8 ohms minus J 120 ohms. So the equivalent impedance then is 24.8 ohms resistance in series with a 128 ohm capacitive reactance. Okay, so you should be able again to see these as the real part, the resistance, the minus J in this case being a 128 reactive value for that capacitor. Show the complete Norton equivalent then for the circuit diagram shown. From the examples 19.3 and 19.14 respectively, I Norton is 34.4 degrees at 121 milliamps, and Z Norton then is 24.8 minus J 128 ohms. So the Norton equivalent circuit then, as shown, is the diagram that we see below. So we have taken our two other examples here and able to convert them into a Norton equivalent here, with all of this being the impedance equivalent, in this case in a Norton diagram. So any load connected between the terminals of a Norton equivalent circuit will have the same current through it and the same voltage across it as it would have been connected to the terminals of the original circuit. The summary of the steps then for theoretically applying Norton's theorem are as follows. So again, this should be something you put in your notebook, keep it for future use. Step 1, 2, 3, and 4, replacing the load connecting to the terminals between which the Norton circuit is to be determined with the short. Step 2, determine the current through the short. This becomes I Norton. Step 3, open the terminals and determine the impedance between the two open terminals with all sources replaced with their internal impedances. This becomes Z Norton, and then connect I Norton and Z Norton in parallel as we saw to give us our Norton's equivalent circuit. So when we come back, we'll hit the last section for this chapter, maximum power transfer theorem.